reverse it. I don't know what the line how it does it correct.
Okay, good. Perfect. So I'm going to be talking about optimization, and I think the first question is why care about optimization? This is me. I'm a math guy by training, so I have a master's in operations research at Berkeley, and then I studied applied math at Brown and got very close to the PhD, but then didn't do it. But my heart is in math.
Anish,
yeah.
Up the volume, up the volume.
Okay. I'll try to project to the back. So the first thing is, why do we care about optimization? And I think the thing is, once you start working with data, optimization is happening. So you may not know that optimization is happening, but it's certainly happening somewhere, either right in your hands or behind the scenes. Anytime you're inferring something, you're going to be doing some optimization. And typically with inference, you're going to be maximizing a likelihood or maximizing some sort of posterior probability or minimizing a loss function. And all these I's means that you're optimizing somewhere along there. So Gustavo talked about OLS regression. So OLS regression is maximizing a likelihood, but there you can do it analytically. So you don't need the computer to do it, right? It's straightforward. But if you take that to the next step and you do something like a median regression, are people here familiar with median regression? So I'll just interject a little bit here and there. So OLS regression, you have Gaussian errors, and it's since the Gaussian drops off very quickly, outliers really affect the results. In a median regression, you have Laplacian errors, so it's a Laplace distribution, and that means you have bigger you have more in the tails, and it's less sensitive to outliers. So it's a more robust form of doing regression. And if you're doing a median regression, this behind the scenes is something like a linear program. That's one way to solve it, but you have to solve it by a computer. If you're doing GARCH, and I know Gustavo at least said GARCH while we're sitting down. I don't know if it was in your slides. Are people here familiar with GARCH? So Tree's familiar with GARCH. So GARCH is a way to, Gustavo was talking about having a stationary series. And with GARCH, what happens is you have a series, but now the volatility is changing over time. So, and this is actually closer to reality. So imagine the stock market, there are times where the stock market is not moving much, there are times where it's moving a lot, and it goes down. And one way to model it is GARCH. And if you want to do a GARCH, you have to solve this using some optimization behind the scenes. So if you do it in Python or R or any of MATLAB, there's going to be a function, but in that function is some optimization. If you're getting a little fancier, you're doing this with a Kalman filter. So people here are familiar with the Kalman filter? Or no? Okay. So Kalman filter is, I think that they first used this to go to the moon. It might have been related to go to the moon. But you have something that's moving around, so you have some dynamics, and you have noisy observations of what's going on. It's this thing that's moving around. So I've used it to denoise series. So I have noisy observations of some series that's happening. And in this Kalman filter, you have parameters. So you have the variance of the noise, and you have things in the dynamics. And you want to figure out what these parameters are to, at the end, extract the underlying series. And to get those parameters, you have to do optimization. The bottom line is, if you're going to be a quant, you have to do optimization. There's no way around it. It's actually something where I think probably over the last 2 decades, at every place I've been, I've ended up doing something with optimization, and it was a way to add some value that someone else didn't have. So I think if you have these skills, you can do things that other people can't do. So you want to learn optimization. That's the first reason for it. Another reason for it is you can build robots. So the word robot, my wife is Polish, and there's a word in Polish called robotnik, which is a worker. And if you look up robot, it actually comes from Czech, and Czech and Polish are very similar languages. And it basically means a worker that you can you can tell whatever you want to do and they have to do it. Right? That's where the word robot comes from. So you can build robots, and what you're going to do is you're going to model something, and after you model it, you can optimize it to do some sort of task that you want it to do. And once you have that, now you have a tool to do the task automatically, and it can do it better than you can do it. So these are some pretty sophisticated robots. Google Maps models how roads are connected together and how long it takes to travel them, and then it gives you the shortest path. Or Expedia will model flights, and then find inexpensive trips. Or if it's optimized for a different criteria, you can find the shortest trip. With portfolio optimization, you model how securities move together, and then you create a portfolio that maximizes the risk-adjusted return. For algorithmic trading, so you model how if you're in finance, I don't know how many people here are interested in finance or come for finance. Maybe a third, so something like that. So once you have a portfolio of some size, you can't just buy or sell things right on the market immediately because you're going to start moving the price. So there's something called algorithmic trading, and the idea there is that if I want to buy a large amount of some stock, I don't just throw it on the market right now. I do a little, and then I wait a little bit, and I do a little more, and do a little more, and I have other things that I'm buying and selling as well. So I can stay hedged while I'm doing that. And I can get a computer to do it, and then the computers can do this much better than I can do manually and control the risk much better. So you can model something, you add optimization, now you have a robot, and this robot is now doing this task for you without any work, better than you can do it, and you can get it to do the task for other people and get paid for it as well. So it's super useful and add tremendous value, either to your firm or to the product or to your customers. Why else would you care about optimization? So optimization puts the learning in machine learning. And if you want to get a t-shirt that says that, you're free to do it. I won't charge you a royalty. So it puts the learning in machine learning, and it actually quite literally puts the learning in machine learning. Yes?
And all this is machine learning, AI, whatever, it's based on large training data sets.
It actually depends on the technique. So
I mean, can it be work on one-to-one relationships? A is related to B because I say so? I have statistical of, I don't know how you count that, is that 1 or 2? A is related to B, B is related to A.
Okay, that I don't quite understand. I don't understand.
Okay, well, you've answered my question. This is outside the parameters of techniques of machine learning and AI.
So if you're doing something logical, then that's a different animal. So where you can deduce that something. So it's a little different. But for machine learning, if you have something like a deep neural net, you need a boatload of data because you have so many free parameters, and there's basically you need a lot of data if you have a lot of parameters. Otherwise, this thing is underdetermined. If you have something smaller, so you could think of clustering. I think is what I think is the simplest version of machine learning. And clustering, you could have 10 points and do clusters on those. So that's not a lot of data. It depends what you're trying to do. And actually, with clustering, you're minimizing a loss function as well. So there's some optimization happening there, but depending on the algorithm, it could be solved heuristic. So again, training means you're minimizing a loss function very literally. That's what training is. And if you're doing a classification problem, like your loss function might be cross entropy, where it's basically you're trying to maximize. So you're minimizing minus logs or maximizing the log of the probability of a correct label. If you're doing something numeric, sort of machine learning regression, you might use squared error, so just the difference between what your model kicks out and the reality. As an example, if you have this deep learning network and you wanted to train it to identify cats, what you could do is start out with a bunch of photos of cats that are labeled. Right? So you have many photos of a labeled cat or not. And I'm gonna feed these into the network, and I'm gonna optimize the weights to minimize the cross entropy. And this is exactly how you would train this network. And if you do this with enough photos, then you'll be quite successful at, and if you had the right network architecture, you'd be successful at identifying cats. So optimization puts the learning in machine learning, and it's literally true. You know, it's not just a metaphor. Okay. Why else do you care about it? Well, if you know something, you get a better outcome. So in the real world, when you're optimizing, the things that you're optimizing, there's no guarantee that you have a solution. There's no guarantee that you're moving at any kind of speed. Basically, you have no guarantees. But there are classes of very well-studied problems. And if you know something about these well-studied problems, you can take the thing that you're working on and say, I'm going to cast it this way as one of these things that's known. And then you can get a solution quickly. You can have a good algorithm. You can have confidence that where you are is a solution. And so you have the well-studied classes. You restate or approximate yours as one. And even if you can't, you know how things can go wrong. So if you know something, you know, my computer's chugging, and the reason it's doing that is because it's in the wrong direction. It's not that it's working. So there's a lot of value associated with knowing something. And how many people here are familiar with optimization? And what sort of things have you done? Sure. So linear programming must be the stochastic programming. So here's the basic setup. You have a bunch of variables that you can play with, and this is what you're going to be changing to optimize your goal. For example, with portfolio optimization, one of these variables could be the percent of your portfolio that's invested in Amazon. If you had a shortest route problem, you could have the variable you want if the road is being used or 0 otherwise. So you have your variables, and then you have an objective function, and this is what you want to maximize. In portfolio optimization, it's generally risk penalized return minus transaction cost minus the sort of other things. If you're doing shortest route, it would be the time from point A to point B, to places going from here to there. And you might put in a penalty on the variability so that you're not only picking a short route, but a route that you can count on being short. Right? And then you have some constraints. And these constraints in a portfolio say you can't invest more than 20% of the portfolio in tech stocks. If we're doing the shortest path, on all the nodes that are at the start or the end, you want to make sure that whatever is coming in goes out. Otherwise, your car is stopping there and just remaining there while you're solving it. So you have some constraints and variables and objective function. And just a quick example. I'll just show you the vanilla version of portfolio optimization. In practice, you'll have something more sophisticated than this, but this is closer to what you'd see in a textbook. And how many people here have worked with portfolio optimization? So we'll say the goal, which is our objective, is to maximize expected return with a penalty on variance and costs. We have our variables that we can play with, which is our decision variables, which is the vector of security ways to be found. We have some initial state. These are our initial position. We have forecast returns. I think Amazon is going to go up. I think Microsoft is going to go down by 2%, say. We have a forecast covariance. This is how I think things move together. And and what the scale is on that. And we have a risk aversion and a cost aversion and some linear constraints. And so what we want to do is maximize the return with a penalty on the variance. It's just the x transpose sigma x is the variance of the portfolio, and then a penalty on the cost, which is the change in the position subject to the constraints. So this is a vanilla portfolio optimization problem, and this is really easy to solve. So this you could, it'll solve in a second. It has a really nice shape to it. It has a really nice structure, right? So the question is, what kind of structures make your life easy? There's something called convex optimization. And I don't know if people heard of convex optimization? Yeah? Yeah, Sri, Gustavo? Yeah. Okay. So convex optimization means, let's say we're doing a minimization. So the function that you're minimizing is a bowl. And what's good about having a bowl is that if you know that when you get to a flat spot, you're actually at the bottom. If it weren't a bowl, you had any peaks, then you might be able to be at a flat spot here, but you're quite far from the bottom. So the first part of convex optimization is the function is a bowl. And then the other part is that the constraints are such that if you took a point that's within the constraint and another point that's within the constraint, then the line connecting them is also within the constraint. And, this makes it very easy to search because you're not going to be going along all that way. It guarantees things about the uniqueness of the minimizer. So if you have something that's convex optimization, it's super easy to solve. Very well understood, both theoretically and algorithms for it. Linear programming is one example of convex optimization. Quadratic programming is another. There's the second order cone programming. I don't know if people have seen that before. It's something I think is more popular in the last decade or so. This is a linear objective, quadratic constraints. And then these are just a few classes of convex, but all the other convex optimizations, which there are many, these are also really easy to solve. They're not as specialized as these three, but the structure is so friendly that general algorithms tend to work on. The note here, programming just means optimization, and the optimization. So you see linear programming just means linear optimization. Quadratic programming means quadratic optimization. And it's an old word, I think from the 50s, that's where it came from, but it has nothing to do with programming. Okay, so that makes life easy. So you know what linear and quadratic programming are. In both of these, you have linear constraints. So this is just a linear constraint on the variables x. And in linear programming, you have a linear objective function. It's just a linear combination of the variables. In quadratic programming, you have a quadratic objective function. And I feel like these are things that you keep pulling out of your pocket when you're doing optimization. So you'll see algorithms at various times. They'll do, if you had something quite complicated, they'll be approximating it as a quadratic program, solving that, and then again reapproximating as a quadratic program, because these are very easy to solve. And people have seen quadratic programming before. Gustavo has. Yep. Mm-hmm. I'm sure he has. Okay. So what else makes life easy? There are different graph problems. Shortest path problems. So this is it. You have distance.
Anish, just to connect the dots. Yeah. If you go back to the quadratic, so maybe just you have a slide on portfolio optimization in that context. Like what is X, Q, and X? Just that'll be nice to just connect the dots.
Let's see. Maybe I'll save this slide up. Yeah. So in the portfolio optimization case, I'm going to run back and then I'm going to remember this slide. Just look at it and remember. this is quadratic right here. And this is linear, and don't worry about this bit. So we're maximizing a linear minus a quadratic. Which is the same thing as minimizing a linear plus a quadratic. So this is the portfolio optimization is a quadratic program. Yeah, that's good. What else makes your life easy? There are different graph problems. Shortest path. I'm in Boston. I can look at all the roads to every city in the U.S. and then find the shortest path to, say, San Diego. And that's an easy problem, well known. They're maximum flow problems. So how much can I pass across a network from one point to another? And that's really well understood. And there are an assorted number of these well-known graph problems that are easy to solve, but they're really specific. So you just kind of have to know them, or if you have a graph problem, you start Googling and then you can look for one of these that's close to it. And if you have it, then you're lucky, and then you're good to go. If you don't have it, then your life can be difficult. Dynamic programming, have people seen that? Dynamic programming, yeah. So dynamic programming, it's more of a principle, and the idea is that the problem somehow breaks into smaller pieces. So if I want to find the shortest way from here to San Diego, I can find the shortest way from here to every point on the Mississippi, say, and then I could find the shortest point from every point on the Mississippi to San Diego. And once I solve these two sides of the problem, it's easy to solve the bigger problem, rather than having to look at every path from here to San Diego. So this is dynamic programming. And you'll see things like this in reinforcement learning. So this setup is very much like dynamic programming. And there's EM. Have people seen EM before? EM algorithms? So this is a really specific thing. And you'll see it in the original application was an estimation where you had some missing data. So you don't know the parameters of what you're estimating, and you have some missing data. And it was a way to solve that, but I've seen EM in different contexts as well. But if you have it, that can make your life easier, because it's really specific. And what makes your life hard? If you have the non-convex objective functions, so you have many extrema. If you have non-convex constraints, if you have integer constraints or variables. So an integer constraint is, say, in portfolio optimization, when you're trading stocks, you don't want to be told trade half a share of Microsoft, or even trade 76 shares of Microsoft. It's better if you get round lots 100 shares, and these are easier to trade. Or if you're doing commodity futures, these contracts tend to be on the order of $50,000 or $10,000, and you want to trade whole contracts. So if someone says trade $70,000, you don't really like that. You'd rather trade 50 or 100. And these are integer constraints, and those make the problem much harder. So anytime you have an integer constraint, it's a hard problem. They're solvable, but it involves heuristics and a lot of brute force, and the complexity becomes way greater. So what do you do when you're outside the easy cases? I should also tell you that I'm trying to give you the idea that optimization is it's not something where you just take what you have and throw it into the computer. You have to finesse your way through it a little bit. So it really depends on the kind of structure you have, and then if you don't have a good structure, that's when you have to get skillful. So when you're outside the easy cases, you can do something called relaxation, which is you have your hard problem, you find something that's simpler that resembles your hard problem, and then you solve that, and that gets you close. and then you're going to repeat this process, keep approximating your hard problem to something simple, and then hope that you get to where you want to be. Another way is to just iterate. So say I'm now standing on the surface that I'm trying to optimize. I don't know how to get to the solution, but I just start walking along, and as long as I'm improving, then I keep going. And at some point where I can't improve anymore, then I say, well, I'm done, and I hope I don't have the outcome. That's usually what's done. So let's say I'm now trying to optimize, and I'm following the gradient, which is just actually the opposite of this. Say I'm minimizing something. The gradient is the direction of the derivatives. And if I go opposite the derivatives, now I'm going down the steepest direction that I can. And imagine I have a machine learning model. So I have n observations, and could be some large number of observations. And I have z, which would be the data. So zi would be the data for the ith observation. For example, zi could be this description of the paragraph in the document that Sri showed, where we want to figure out what is the sentiment in this thing. So zi is the description of that. And y is the label for that observation. Sentiment is good or bad, something like that, plus or minus. And x will be the parameters to be fit on the model. And g is what the model outputs for the observation. And I'm going to try to minimize the loss function, which is what I know the label will be and what the model outputs it to be. So how can I do that? I just start at some point, and let's say I go down the gradient. Traversing down the gradient. What this is. This used to be called steepest descent in the optimization literature, and it was regarded as a really bad idea. So I have a master's in OR from way back when, and someone said they were doing steepest descent. We would say, oh, look at this stupid person who's doing steepest descent. It's a really bad idea. And the problem with that is that it's really sensitive to scale. So if you imagine that one variable is measured in feet and the next variable is measured in miles, the gradient for the thing in miles is going to be very big. So this is the change in the objective function per mile, where the other one is the change in the objective function per feet. So it's sensitive to the scaling. And what you really want to do is take the inverse of the curvature times gradient. And this is the right way to do it, according to the literature. But steepest descent has reappeared now in the machine learning world as a stochastic gradient descent. Have people seen that before? The stochastic gradient descent? I'm sure you've seen it. And this is, I think, now how all the deep learning models are fit.
Yeah, it's one of the choices available. And there's Adam and a bunch of other optimizers, but SGD is like typically the default choice.
Yeah. So if you look at a paper, most likely they're going to start talking about stochastic gradient descent on it. And it's the same steepest descent idea. So this is the thing we want to minimize, which is the sum of the loss, where you get to say the average loss. And what stochastic gradient descent is doing is saying, so this is a ton of data, n is very large in the big data world, so n could be thousands or millions of points. This is very expensive to compute. And what stochastic gradient descent is saying is, I'm not going to use all the data. Let me just grab a point or a few points, and I'm going to improve my guess based on those. So rather than taking a gradient of this, I'm going to take a point at random, and then follow the gradient of that one point. This is computationally very efficient, and it happens to work as well as steepest descent, except for the final refine. So next thing is, how can optimization go wrong? Well, you can stop at a local extremum. So you're at a flat spot, but it's not the best. It's not the minimizer or maximizer. If you have a wrong algorithm, you can go very slowly, and it can be extremely costly. So I know where I was, our AWS bill was in the hundreds of thousands of dollars a year. So it's expensive. And if you have a bad algorithm, you're going to be burning this out. And the other way is, even if you have the right algorithm, if you have noisy data and you're not accounting for it, or you have lots of degrees of freedom, you're going to end up with poor out-of-sample results. So you overfit the data. This is something you have to take care of. So, say you have noise and overfitting, what can you do? So I wonder, have people here seen regularization before? Yeah? No? Yeah. Have people here worked with the deep neural nets?
Not yet.
Not yet. Oh, yeah. When they go to this workshop, by the way, I think you see it a lot in the deep learning, the regularization. So we want to minimize some sort of function. X is our decision variable. Y is our data that we're using. That's part of the function. And let's say Y is noisy. So what can we do with that? So there's something called robust optimization, where we say, let's find the best worst case. So we're going to, rather than minimizing f of x, y, we're going to minimize the worst case of this thing, where y takes a range. So y is no longer fixed. This is my data. Y can be in a range of things. And what's the worst that I can do? So I want to raise my floor as much as I can. Another way is regularization. And this is, I think regularization is, it's old, probably to the 1960s, or maybe even older than that. It's related to ill-post problems and inverses, and penalize the norm of the decision variable. So I'm minimizing f of x, y, and I'm going to add a penalty on the norm of x. So I want to create large coefficients. This is the same thing as a ridge regression or a lasso penalty. Have people seen ridge regression before? And maybe you've read about lasso penalties. Yeah, so the lasso penalty. And this is very tightly connected to Bayesian statistics. It's basically, ridge regression is the Bayesian idea. Lasso penalties tied to they're Bayesian ideas in optimization. Just a little more on regularization. In portfolio optimization, this happens to be my idea, my baby that I worked on for many years. There's uncertain covariance, and it's patent pending. Uncertainty can penalize utility. So rather than just maximizing the expected utility, I put a penalty on the standard deviation of the utility. And this would be a regularization on that. In deep learning, there's dropout. Have people heard of dropout before? Yeah. Okay. So deep learning dropout, basically you have this network that has many, many connections in it. And when you're training the network, you just throw out, randomly you're throwing out connections and training the other ones. And that way you're going to spread the information across the network, and you're not going to overfit things too much. And this is a regularization idea too. It just takes, you might think of it as putting some sort of penalty on the number of connections that are used. Some optimization tools if you want to do this at home, and I think you really do have to do it at home if you want to get it in your bones, is to get some of these libraries, solve a few optimizations, and then it becomes pretty automatic. There's CDXOpt, which I think the guy is at Stanford. Sure, do you know CDXOpt? The guy's at Stanford? Boyd is Boyd. CDXOpt NLOpt is a library that's owned at MIT. CBC is for mixed integer programming. There are Google OR tools, and they have linear programming and some of these graph algorithms, the shortest path, maximum flow, minimum cost flow, how much how many items can you put into a knapsack, like that. And then there's Cplex, which is a commercial optimizer for really hard problems. And it's a different beast, but it's expensive. But if you have a very, very hard problem that you need to solve, that would be the way to go. And I think MATLAB has an optimizer as well. And just some applications in finance. There's portfolio optimization, which you see in algorithmic trading. If you want to do an index tracking or construct an ETF, for example, there were these inverse volatility ETFs, the inverse VIX, and that's something that would be too hard to construct using an optimizer. If you want to hedge a position with an optimizer, if you're doing asset liability matchings, for example, you know you're going to be on the hook for certain cash flows in the future. So you can find assets that give you the cash flows to pay those liabilities, minimizing the risk and the sort of criteria. Nowcasting covariance, this also happens to be well standard in mind. The world is constantly changing. There's a lot of current information happening. For example, finance VIX is an implied volatility indicator, and when it spikes, the market is suddenly more volatile. It happens instantaneously, or there's news that's happening that's instantaneous. So there's a lot of instantaneous information, and using an optimizer in this information, you can get a view of covariance that is as of now, and it's not dependent on history. It just has some value. And then I'm going to see one last slide, and then we'll show an example. So optimization is everywhere, especially as there's more and more machine learning. And I think if you want to be a quant, you have to know it. It's going to end up in your hands at some point. I think the hedge fund where I was, a guy on the board who was the president of the American Investors, he said that he was at an offsite. This was near the end of his tenure, and he said to all his colleagues, he said, "You realize we wouldn't be quants today. We wouldn't make it because it's a different set of tools. And optimization is definitely one of the tools. If you know something, you can add a lot of value, and add a lot of value means it's fun to solve problems, it's fun to create something, it's fun to get paid. You can add a lot of value, and there are still puzzles to be solved. So I don't think the optimization piece of machine learning is fully mature. I think it's still developing, and if you're into research, there are things to research, which is kind of nice. And Sri, can we pull up this and see the portfolio? Yeah. Second. While this comes, did anyone have any questions on this part?
Yeah, finish the Q&A and then we'll do the demo.
Okay. So this is it for the slides, and we can do demo. But are there any questions about optimization that I might be able to?
So this is the Q sandbox, which basically has these applications which are running. What we have done is we have just encapsulated all these environments, including the experiments, into projects. And when we do these workshops, we'll kind of give you these projects so that you can start from a place, kind of iterate through it, through data, and putting in the logic, and then you can see running the application stand. So it's supposed to be a different environment. Okay, so the first application is, so as you can see, we have multiple applications running in the same environment. We have some MATLAB applications, some CVX applications, some Google OR tools, everything running in a single environment. So this is the CVX course. We're going to fire up a Jupyter notebook on Amazon. So everything is configured here, so you don't have to worry about any installations or anything, but I'll give you the links on where you can potentially go and try stuff out. I don't know why, even after saying once that I don't want to save anything, it just keeps asking me for the password. So this is the CVX short course. So Stephen Boyd, who's a professor at Stanford University, their group have put together a bunch of open source packages which could be used for structural optimization problems. So this one's the short course they ran, and one of the applications is portfolio optimization. Do you want to walk through it? Or?
Yeah, sure. And this is, so there's a notebook online for CVX portfolio, and this looks richer than the notebook on the CVX portfolio. This is modified, yeah?
So there are like two ones. So okay, I'll walk through this one, and I'll let you walk through the other one. Okay. So CVX is basically a package used for structuring optimization problems. So in this particular application, there is a bunch of different use cases. So here we are looking at the portfolio optimization problem. So Anish showed the math on how do you structure these. So the asset returns, and this is the classical optimization problem, right? So you are expected to compute the set of weights which satisfies this particular criteria. So basically all the weights add up to 1. So it's an allocation like how much are you going to be investing in various assets, right? And this is a Python-friendly package, which means you can write your code in Python. So if you already know Python, you can just fire up your optimizer and run through it. So you import the CVX package, and we are just importing a bunch of other libraries for structuring the data and plotting these libraries. So here, instead of getting the data from the markets, just because they're academics, they've just put together an example where it's randomly generating some data, and then they're setting up what's called as a long-only portfolio, basically saying the weights add up to 1, which means that I'm not going to be shorting any stocks. I can only allocate, if I have $100, I'm going to be like allocating it to different assets, and I'm not going to be selling something and then.
You actually can't short with this one.
Well,
You just have to be in the net.
Right. But in this particular case, they are setting up a long-only portfolio. So
okay, so it's not negative.
Yeah, in this particular case, they're using long-only. Weights are all greater than 0. Yeah. So the weights are all. I mean, these are like the constraints you're setting up. So here, it's a long-only portfolio and positive. So then the weights are greater than 0. And this is the problem. So you set up that you want to maximize this, and then you compute the trade-off curve. And this is what's called as an efficient frontier. And these are like the inefficient portfolios, and ideally you want to have a portfolio on this particular line. And then they have some additional characteristics, and if you have portfolio constraints and different constraints, you want to have market neutral, so you can set it up, and then you can see how various portfolios perform. And then this one's just to kind of illustrate that you want to have different with various leverage limits, how will the portfolios perform and other variations. So they've kind of just given you some samples on how you can use QP solver, as we call it, quadratic solver, to basically structure a portfolio optimization problem. It's all structured in Python. It requires you to install just this one package. called CVX5, and you run through it, and you basically can reproduce these results. Okay. So I will share some links with you afterwards, so you can replicate it. You can just go and download the packages if you want. The one you were looking for, Anish, is here. Is that running, or you still need some time?
Yeah, it's running.
It's running?
No, it requires some time.
It will require some time. Okay, we just started the CVX portfolio. It's going to take a little bit of time, but so this is like the GitHub source code, and in the examples, have different kinds of portfolio optimization problems. So single period portfolio optimization problem, a multi-period portfolio optimization problem. So let's look at a single period optimization problem. So this is basically what you wanted to talk about.
Okay. Which is more or less, this is going to be very close to what you saw before. So you're optimizing a portfolio. Sigmas is your covariance. Returns are your return forecast. Volumes are, if you want to do transaction costs. And these functions are a bit complicated to explain. But what it's doing here it's just looping through optimizing a portfolio with different scalars applied to the risk, so different risk-return trade-offs, and also different scalars applied to the transaction costs, different transaction cost penalties, and constructing some sort of like an efficient frontier, but based on transaction costs as well as risk. Essentially the same.
Okay, cool. Let's start with this.
Sure.
Are you able to choose the algorithms that you want to use for the optimization?
In this one?
Yeah.
I didn't know. But
Well, in the CVX portfolio, you can. In the CVX package, you can. I mean, like you're basically, this is just a QP problem with additional, you're going to put in your penalty function in the same thing, and then you can set up your constraints. There are general optimizers where you can set up any optimization functions, linear optimizer, quadratic, whatever you would want. I'll show you some more examples and just kind of give you a sense of if you are wanting to generalize your optimization problems. So one thing you could potentially do is, in the same example, there is this. This was not on my radar, but a good friend of mine who also got his PhD from Northeastern a long, long time ago, who has the same first name as me. He and I, we connected after a long time, after close to a decade. But I asked him what have you been doing, and he said, like, well, I've only been settled down in like the southern part of the United States, Atlanta, Georgia, Florida, and that's where I'm kind of hanging out nowadays, warmer weather. So I asked him, like, what have you been doing? And he said, well, I've worked for Disney and basically help optimize their, all their rights and things. So we wanted to kind of, figure out like designing of various rights, how fast should it go, how slow should it go, and how much, putting all those constraints and running optimization problems and simulations. Working for UPS and helping them set up their logistics and scheduling and making sure that they can, do interesting aspects there, and working for a bunch of other supply chain, robotics kinds of companies. So I asked him, like, what have you been using for tooling? And he said, well, we tried different packages, but one of them is what's called as Google OR Tools. And Google OR Tools is basically a package which you can just go and download from the Google site. There's the GitHub code. It's completely open source. You can go and like review stuff. And when you go in there, you can basically look at different kinds of examples. So let me show you some of the kinds of problems you can potentially solve. So in here, you have a listing of all the problems which they support: linear optimization, constraint optimization, integer optimization, routing, bin packing, network flows, assignment, and scheduling. So as you can see, all these are interesting problems depending on. So the point I wanted to emphasize in the morning discussion with data science is, it's never always about just prediction. Right? there are so many interesting data science problems. You have to be able to define what kind of a problem you have in mind. What are you trying to do? So for example, here you may have an employee scheduling problem. So, you may be thinking about, well, organizations working employees multiple shifts. You need to schedule sufficient workers for each daily shift. These schedules have constraints like no employee should work more than 2 shifts in a row. How do you actually set up that kind of a problem, right? Or it could be like a job shop problem, wherein this was something I used to do a lot in my mechanical engineering days when I used to design hydraulic excavators, because we were in a job shop and we had like sequence of tasks. This cannot start before this other thing already has been completed. We have a set of machines. We have specific outcomes we want to reach. So these are like the kinds of constraints which typically are not expressed in mathematics initially, but will be expressed as business constraints, right? So no task for a job can be started until a previous task has been completed. A machine can only work 1 task at a time. A task once started must run to completion, right? So think of these in the context of data science pipelines, wherein certain tasks could be parallelized, but certain tasks has to be sequential, right? For example, data scraping. I can't start pre-processing my data till I have processed all my prior data sets. I've scraped all my data sets. I've ingested all my data sets. So all those are interesting aspects of how you want to optimize your particular pipeline. Certain things could be parallelized. Certain things have to be sequential, right? And then there may be constraints where a trade has to go every half an hour, or you have to let go of your entire portfolio by the end of the day. So those are all the specific constraints you'll have to mention, and you'll figure out what kind of problem to structure. So in this particular case, they're structuring this problem, and they're setting up this is job 0, job 1, job 2, machine 0, machine 1, machine 2. How do you actually structure this kind of a problem? So I would recommend, this is, again, not many people go in and read these because it's pretty technical, but these are really interesting problems. So I highly recommend you to kind of go in and understand these problem statements, because I have a lot of applications, not just in engineering, but also in structuring data science applications and data science problems. Yes, please.
You mean I have to put my pants on before I put my shoes on?
Well, you completely threw me off track. I just kind of remembering what is like
Machine
the thing I've learned.
Step A has to finish before step B starts.
Right. Yeah.
Just from a different angle.
Yeah, it's winter, and it becomes handy when you're like wearing your snow gear for skiing. But the way you structure these problems, so I'm going to show you how the code looks. Once you have the problem definition in mind, what you're trying to do is you have to structure this into a mathematical optimization problem. So you have to be specifying what the objective function is, and then what are the variables and what are the constraints, and how would you structure this. And they are giving you like tools, and in this OR tools, you are basically invoking that function. They're specifying the job data in a particular format, and then defining the variables and the jobs, and defining the constraints, defining the objective function, defining or declaring the solver. This is where you choose your algorithm based on the problem you have in mind. And then you can look up all the results, and you can kind of visualize these results. So this will be like your optimal schedule, right? So people would pay thousands of dollars for these kinds of solutions just 10 years ago. Okay, you would at least pay like $2,000 to $3,000 at least a year just to get access to software like this. And the power of open source is you get these tools more or less for free. But the question is, will these tools give you the solutions you're looking for? And that's where the things Anish was talking about, because you can't just basically throw your data at something like a black box. You will have to kind of structure the problem, define the objective function, define the constraints, think about whether this actually matters, regularization, key aspects of structuring all these algorithms, and then go about building out your solutions. And that's where the data science acumen comes in, the practice and the best practices come into play. So I will share links for this solution too. But whenever, so I was talking to my friend, as I mentioned the other day. So I asked him, so did you guys deploy the solution? And they said, no, we prototyped it, but we did not deploy it. And I asked him why. And he said, well, I had to restructure some of my problems and I had to redo some of the way in which some of the optimization problem has been structured and convert my objective functions to different kinds of functions. Only then it would solve. So there was a lot of iteration, there was a lot of trial and error which had to be done. And then when it came to like finally releasing it into production, these tools potentially gave them really good results, but with real large data sets. So a lot of times you may have to think about, well, I need to move back to a commercial tool in order to do that. And just to give you an illustration, so what I've done is we have a partnership with the MathWorks guys. So we've also integrated MATLAB. So that way, in case you wanted to try out a similar problem in MATLAB, because you also have a lot of interesting case studies and examples you can potentially learn from. So that's what's being launched here. So here, just to give you a perspective, what's happening now is we have, as you know, I'm not installing any software on this machine. Everything is based on a browser. So we have a license server running on Amazon Cloud. We have MATLAB installed on the cloud. And Amazon Web Services have something called as AppStream, which will let you launch any MATLAB, any Windows-based applications. We're kind of tying all those aspects together, and we've built out a whole pipeline, and that pipeline is getting kicked off, and we kick that pipeline off using the sandbox. And we are now bringing in the data, the algorithms we wanted to use, and I'll give you a simple example just to kind of illustrate. So we are kind of putting everything together, and we're launching it. It's usually going to take like a minute or so, just because it's on the cloud, and things, you need to be patient when things run on the cloud, because it's not just launching instances. You're kind of grabbing data from multiple places, putting everything together, packaging it, and then making something available. So what you're seeing now, this whole process, if you had to do it manually, would at least take you a couple of hours. The installation of MATLAB and kind of getting all the data, setting it up, testing it, and everything. But it takes a couple of seconds, and it kind of just fires up. So from a learning perspective, you can get to the actual usage as soon as possible. So here, just to give you one more flavor of how you can run your optimization tools. So this is the optimization toolbox. So they have a bunch of different problem statements. So in here, so you can see different kinds of optimization examples: traveling salesman problem, factory job allocation problem. So this is like the mixed integer quadratic programming problem. So this is where we are using a mixed integer linear programmer. And then here, I can just open this. So this gives me like MATLAB code for running this particular example. And similar to a Jupyter notebook, you can actually run this whole thing in the browser. So here again, this is the MATLAB syntax. If you are not comfortable with using an open source project, I mean, some companies do not want to use open source products. So here you can potentially use a commercial product, set up the optimizer, and then here we are setting up the whole specifics about the MILP problem, and then you can run this. So let me see if I can run it. So if I run the whole thing. It's taking a little bit of time. Okay, so now you can see, let me just undock this. So you can see that this whole thing ran on the cloud, and you are running each one of these cells, and here you can see based on the iteration number, we are kind of using an approximation, like what I mentioned my friend did for a problem. So you're kind of taking the quadratic approach and you're converting that into a linear approach. And this is basically as you kind of go from increase the number of iterations, they kind of converge based on the number of iterations. And this is like the optimal asset allocation setting based on the proportions. So you can potentially try this example out also. Okay. There are a lot of different optimization packages. In fact, if you go to any Informs conference, You're going to see a bunch of players in that space. Gurobi is another one. Gurobi. There's a meta programming language called Ample, which is used to like structure optimization programming languages. So this is typically what operations research folks do, structuring and running optimization problems. But there is a lot of confluence between operations research and data science nowadays. So when you talk about data science, the phenomenon, I call it the MOOCification of data science. People look at somebody's tutorial, change the variables, put together a 2-minute video, and they just sit in front of the computers, keep looking at how many likes do I get in this video. I shared another supervised learning problem, and I shared another clustering problem, and it just basically keep looking like how many likes do I have? Is my video getting viral? So people have stopped solving real problems. They just kind of recycle somebody else's material and keep working on it. So that's not a good way of learning data science. You have to kind of expand the scope of the problems and be able to design and run these problems. So while I'm in here, I want to emphasize that the applications of data science, I just want to connect the dots to what Gustavo was talking about. So we didn't really get a chance to talk about some of the applications in the econometrics area. But there is there's a block called as the Liberty Street block, which is the Federal Reserve Bank of New York's blog. And the researchers out there, they're all econometrics and time series specialists. So they basically are in the profession of predicting, where we are going with respect to economy. And if you've been listening to the FOMC minutes and Jeremy Powell's statements and what's happening with the economy, and all of this, goes through a lot of rigor. And what the Liberty Street economics, Liberty Street is basically where Federal Reserve Bank of New York is, so that's why it's called Liberty Street economics block. So here, they announced a few months ago that they're going to be open sourcing their nowcasting code base. So the nowcasting, they actually have a report called as the nowcasting report, which is released every often. So you basically look at the GDP release, what was postponed. So they're kind of putting together like a report and over time, how things, what is the nowcast for, then this is like the Federal Reserve nowcast for the various data releases. And then they kind of provide you the different levels of detail. So when you kind of look at these numbers, you would be wondering what kind of tools did they use? How did they come up with these estimates? And these are all time series based applications, right? They probably got a lot of questions in a similar mode. So what they did was they basically said, well, I don't want to answer any more questions. We'll just open source the code. So they wrote a blog post on the Liberty Street blog, basically saying, opening the toolbox, the nowcasting code, and they just put it on GitHub, saying that this is the code we actually use to go through our analysis, and this is how we put together macroeconomics, and this is visualizing big data. When we talk about big data, it's not just downloading a Kaggle data set. This is big data in action used by our economists to predict the economy, to kind of generate the metrics we hear on a regular basis, right? So this is how they kind of visualize things, and these are like the common factor which captures the bulk of co-movement with respect to the data. And all these reporting aspects, you can see like a lot of people work on it. To make it easy for you guys, we just basically put this whole thing together as examples in the
Question is those numbers, is that still running now?
So this is the nowcasting example. So as you can see, they have written everything in MATLAB. They've given you a snapshot of the data set. So in terms of reproducibility, if you are Gustavo working, I don't know, 5-10 years ago at the economic consulting house, and you want to figure out whether these analysts are doing a good job, or should they come up with other models, or do you have other opinions, you could potentially just take this code, run it, and you can actually see what the Fed guys are actually using for their analysis. Okay, so as you can see behind, you can see all these details of the tables. Now, in the time series workshop, we're going to go through some of these examples in more detail. Unfortunately, we don't have the time kind of looking at that. So you see like the model specification, what are the various key elements in the data, how are they kind of tied all together, and what's the nowcast for the specific GDP. And you see the whole thing. And in this particular case, I think there were some graphs also. I don't know why graphs didn't pop up. But anyways, you get the idea. So you can potentially use, these tools to just, build out different kinds of estimates. Okay, so I just wanted to give you some examples on what is potentially feasible. Any questions for Anish, me, or Gustavo before we end the session? We'll take another 3 to 4 minutes of Q&A, and we'll take a quick break, quick coffee break. Yes, please.
So I have a question about the general machine learning and optimization problem.
Yeah.
So we all know machine learning is very good at interpolation to exploring the data. We have data. So, but what if I want to go a step further? I want to do the extrapolation. Are there any techniques to combine machine learning and function form which are good at extrapolation to do so?
So you want to take a stab at it?
No, I think it probably depends on the technique. It seems like.
First of all,
Go ahead. I'm thinking about it right now.
I would disagree that machine learning is good just at interpolation, because we are not just always trying to approximate the functional form in the context of machine learning. The major objective of machine learning is to be able to build a generalizable model which can be inferred from data you have seen till now, which is really good in the context of prediction, which is basically extrapolation, right? So the way we structure the problem, it's not just fitting, it's not statistical analysis where you're trying to figure out, what is the functional form which works best for this particular data, right? And that's the thing I just want to know. We are trying to build this generalizable form, which we could say, well, had I used this model for prediction in the future, which is basically what we're trying to do in the future is exploration, can we see the same results which was actually realized? Or how close could we get to the actual results which was realized in the future? Which means that we have to define those metrics to say, am I okay with living with this amount of error, right? In the context of optimization, your goal is different, right? I mean, like, it depends on the problem you're having in mind, but when you look at the machine learning problem, it is an optimization problem in ways because you are minimizing the loss function. The loss function is what defines the metric to tell you how bad or good the result is. And your goal is to come up with the best generalizable form, parametric or non-parametric, to come up with the best possible loss function, metrics for the loss function. And that's going to give you a weight. So that could be structured as classic optimization problem. Even simple regression, ordinary squared, sum of squared errors is basically your loss function, and you minimize that loss function, you're going to get the functional form of your regression equation. Right?
I think it depends on the technique. So something like the k nearest neighbors, which you might know. So that surely can't extrapolate because it's taking the nearest points. But I think something with some, that has coefficients on it at the perimeter would be doing some sort of extrapolation.
So what if I want to do very long stretch prediction? For example, if we have a model that is its model output is related to interest rate, and when I do the risk neutral pricing, especially for very long-term instruments, probably we need to go for the 10 years, 20 years. I'm not inputting the actual interest rate because it's just risk neutral patterns, and it's going to be very far away from what I have data is. It's a far extrapolation. Do machine learning offer any benefits beyond the traditional parametrics model?
Yeah, it's a loaded question.
I would guess no.
Yeah, I mean,
it's so uncertain at that point.
So
That's my.
I mean, that's where you have to look at a different modeling technique rather than just machine learning.
Yeah.
simulation is the reason why people do, predicting 30-year interest rates, 20, 30, it's all prominently driven by bootstrapping and simulations. I think those would be, even to backtest, how can you backtest everything in terms of economic shocks and market events, and all those things to predict something in the future that long? I'm not sure if you can even factor those in as variables which are going to influence your outcomes.
I think there's another side to it too, which is if you're looking at images, you have an enormous amount of data. You have as much data as you want. So if you need more data, you can get more images. But if you wanted to do something, say interest rates, what do you have? 50 years of data, or relevant data, and you can't get more of it. So you don't have the really big data. And then the other thing is that, and this happens, I think this is constantly happening, that people try to apply machine learning in finance fairly, coming from success in something more physical and then saying, I'm going to apply it to finance. And the thing is, the financial markets are constantly changing. So even if you have 50 years of data, how many years of data are relevant? Not that much. And I remember you were on a panel late this summer or something like this, talking about who was the guy?
David Kane?
Yeah, David Kane's panel. And so David Kane was asked everyone, do you believe in deep learning and finance? And I kind of shook my head and said, no, not in terms of doing the stock price. And Sri had a good point, which is in finance, it sort of enters in all the things that you can use to predict the stocks. So the hedge fund that I was at looked at ship movements, and then would make predictions based on the ship movements. Now, something like that, you can use the machine learning to figure out what's going on with these ships, or lots of the inputs into figuring out what's going on in the markets. But I feel like markets are constantly changing, and even if there weren't, there's not that much data.
Okay, any more questions before we take our break? Okay, cool guys. So we will reconvene for the final session at 3:05. 3:05. Thank you.